I have built Tetris in Python. I've been learning to code for 2 weeks now, and my goal was to build projects without the use of tutorials or AI. And 2 days and a lot of desperation later, this is how I did it. As a first step, I rendered a single block on the game field to verify that the grid system worked correctly. The draw function iterates through every x and y position of the field and checks whether it matches the block coordinates of block x and block y. If it does, a square is drawn. Otherwise, an empty space is printed. The field borders were essential because they clearly define the edges of the game area. Without visible edges, it was difficult to distinguish where the field started and ended, making it harder to verify whether the block has been rendered at the correct position of the grid or not. To create the falling effect, I implemented a game loop that continuously redraws the field. Before each frame is drawn, the OS system's CLS function clears the terminal so that the previous frame disappears. This creates the impression of an animation. The vertical position of the block is stored in the variable block y inside the loop. Block y is increased by 1 after a short delay. As a result, the block is rendered 1 row lower in every frame, making it appear as if it is falling down the screen. The next goal was to make the blocks stay at the final position so that the new blocks could stack on top of them. The main challenge was detecting the exact moment when a block was no longer allowed to move down. Once this condition was met, the block had to be permanently written into the field using this function. Understanding this line was initially very difficult because 2 square bracket pairs are used in 1 row. However, the syntax allows the program to access the exact position of a block segment and replaces it with a permanent block symbol. After implementing this logic, blocks successfully remained in their final position and stacking worked as intended. The next feature I wanted to implement was the movement to the left and the right by pressing the A and D keys. To achieve this, I used the MSCVRT library again, which I have already used in my Snake video. It allows me to actually detect a keyboard input in real time without stopping the loop. The function mscvrt.kbhit checks whether a key has been pressed, while the getCh function reads the pressed key directly from the keyboard buffer. The input is then converted into a character and compared against predefined controls. Before moving the piece, it checks whether the new position would exceed the left or right border or collide with any already placed blocks. Only if all the segments can move safely is the x-coordinate of the figure updated by increasing or decreasing block x. At this stage, it was actually time to implement the first Tetris figure. I decided to start with the zigzag shape, I don't know what you call it actually, because it contains multiple connected blocks, and I thought it was a good test case for the coordinate system that I implemented. A rotation feature will be implemented later, but the initial goal was to simply verify that the grid concept worked as intended. Before adding more complex mechanics, I wanted to ensure that the figures could be rendered correctly using the coordinate system. The grid is based on an XY coordinate system, where the X increases from the left to the right and the Y increases from the top to the bottom. Each block segment of a figure is stored as a coordinate pair inside of a list. For the zigzag figure, the coordinate system was defined as this. This means that the figure occupies 4 cells in the grid. The first block is placed at 0, 0, the second at 1, 0, the third at 1, 1, and the fourth at 2, 1. This allowed me to actually put the shape in the game. After successfully rendering the zigzag shape, I applied the same approach to the remaining Tetris figures. Each shape was defined as a collection of coordinate pairs and stored in the figures list. The next step was implementing a rotation. To achieve this, each figure was stored as a list containing multiple coordinate layouts, where each layout represented a different rotation state. When the player pressed the rotation key, the program switched to the next coordinate set and rendered the updated shape. During testing, however, I encountered a funny issue with one of the rotations. The coordinate layout of the T-shape and one of the zigzag shapes had been mixed up, causing the wrong blocks to appear in the terminal after rotation. As a result, the figures are no longer match their intended shapes, and this kinda looked funny to me, not gonna lie. Fixing this error was actually a bit more difficult than I expected because it was hidden inside the coordinate definition. To debug the problem, I had to manually draw all the affected rotations on a piece of paper and compare the coordinates with the rendered output. After that, I was able to actually fix the coordinates so that the rendered display looked correct. The next feature I added was the next piece preview window. The idea was that the next piece figure should already be visible before it enters the actual game field. For this, I created a next figures list with a random choice of figures. This means that the program randomly selects one upcoming figure and stores it separately. The function getPreviewLine then creates a small preview field and renders it to the next figure inside it. The preview uses the first rotation of the figure and then places its blocks into a small area. When the current block can no longer fall, the program takes the next figures list and makes it a new active figure on the main field. After that, a new random figure is selected again and stored as the next preview piece. This creates a cycle. One figure is active in the game field, while another figure is already waiting in the preview. And as you can see, the game result is actually a functioning game. We have a preview window, we have falling pieces, we can rotate them, we can move them, and we also have a scoring system implemented. If you enjoyed this video, hit the like button. And if you want to follow my journey from complete beginner to employed developer, make sure to subscribe. And I see you in the next video, until I get employed.